welcome. I'm going to show you a little bit about how to create your own clang-tidy checks today and how you might be able to do them in the future. So I'm Stephen Kelly. I'm around the internet under Steve Era. So most of the places you see Steve Era in a programming context, it's me. I'm not the horse racing one, so just to clarify. This is not working. So the alternative title for this talk is Refactor with Clang Tooling, just because I like the imperative nature of that title. So my background is, I kind of started programming with KDE and with Qt and with CMake. A lot of open source stuff, but kind of over the last 10 years has been my way of learning C++ and learning how to do programming in a professional context. Most recently, I've been looking into Clang, how to use Clang tooling. But I also want to point out that I'm not a compiler engineer. I've never taken a course in college about compiler design or anything like that. I couldn't tell you the first thing about what's important about an AST. I graduated from mechanical engineering, so when I left university, I thought a translation unit was a meter. So I've been shown to be wrong. So today, I'm going to show you a little bit about what clang-tidy does, in case people don't know. I'll discuss a little bit about why you would do mechanical refactoring for your own code, for your own bespoke needs. Because mostly I want to show you that that is possible. You know, it would have come to your mind already, but it becomes a lot easier once you have compiler tooling such as Clang tools. But there are problems that you encounter when you try to do that, and I'm going to show you what might come up and how you get around them. So I don't want to dive too deep into the details of clang-tidy, like the command line API and stuff like that. I'm also not going to tell you how to create a compile database, which is a necessity if you're going to run clang-tidy over your own code base. There's other resources for that. So these are the takeaways that I want you to take away from this talk. Just that it is possible for you to do large refactorings in your code. Don't see them as blockers to improving the maintainability of your code. So tools, tips, tricks, and traps is what I called this. So looking at a few tools first, the clang-tidy tool itself has, well, I guess 6 months ago it was 240 odd checks. Some of them are not relevant to you because some of them are vendor specific. So because clang-tidy has no plugin system, you have checks in clang-tidy for Abseil and for Boost and this and that, which may not apply to your code because there's just something about the developer policies for those libraries. But there's dozens of checks which would be useful for your code, particularly the ones starting with modernize. If you want to modernize your code, this is a nice automatic way to do that. So here's some code. Does it pass code review? Assuming this is a new project you're writing today with a modern compiler. Pass code review? No. People say no. Why? It's probably because this does not have override on the end of it, and maybe you want to get rid of the virtual as well. So, was somebody chuntering from a sedentary position there? No, okay. So you can run, is that working? You can run clang-tidy checks now on Godbolt. So I've pasted in the same code. And the way to enable this in Godbolt is you go here and select clang-tidy as a tool. And then this pops up. So we can write our own options that we pass to clang-tidy. Here I'm passing modernize, use, override. And you can see in the output, it's pointing out that this function doesn't have an override decorator, and probably it should. And it's saying virtual probably shouldn't be there. So if I add -fix, clang-tidy will actually make the change. If I put a dash in there, will make the change in my original godbolt source. So you can undo and redo and see that change. So we can run multiple checks at the same time. So if I get rid of fix here for now, and just write comma, modernize, use null putter, it will additionally give me a warning or a diagnostic about the 0 and say that should actually be null putter these days. So again, -fix, and the godbolt source changes. Cool, so that's clang-tidy. It's doing automatic rewrites of my source code based on semantic understanding of the source. So it's not just doing text replacement. So just an example of what you might want to do in your code is maybe replace an old type with a new type. This seems to happen a lot with strings because it seems every project has their own several string types. So maybe you want to port away from the old string type to the new one because it's better for some measurement of better. So this is a pattern that you will find in your existing code. And I think with a sed script and maybe a bit of Python, I'd be able to port that pattern to new type, no problem. This maybe, it depends what called function returns. Maybe that returns other type and there's an implicit conversion. So maybe I would have to, if I change this to new type, I would have to write to new type on the end here. But I think with sed and a bit more Python and cleverness, I'd be able to port 80 or 90% of those in my code base. But it gets harder and harder. So if I want to replace both of these with new type, maybe I'd be able to do that. If it's other type, then I would need to realize that on this line, the return line, the type is changing, and I need to add a .to new type here. And to do that, my tool needs to understand the return type of the function that it's in and the type of the variable. I don't think I could do that with just text processing. Another example is just the inverse of that, so just the reverse. Another is, say we have some member variable and we want to change its type. And so in our source code, we're initializing that somehow. And maybe this needs to become some function dot to new type. But in my text processing tool, I only have this as context. So I would need to somehow process all of the other code in my translation unit, figure out that bar is this struct and it has this field with that name and it's that type, etc. So I don't think I could do that with text processing. But that's exactly what these Clang tools are for. And just one more example. Here, I have the requirement that I want to rename get to make some type. The problem being that I have other methods called get in my code, and it's only get on A that I want to port. So again, that's exactly what the Clang tooling API is for. So we can use this system to do large-scale refactoring, where it's not practical to port using text processing tools, because Clang tooling has semantic knowledge of your C++ code. It knows that you're calling functions. It knows that you have binary and unary operators. It knows what a pointer and a reference are. We can automate this. We can put it in our CI. We can fail if there's new diagnostics about anything, so we can enforce that people don't start using the new or the old type in new code. And we can hopefully write this in a way that we don't break existing code, even though we're changing a lot of code at the same time. So the workflow that we would use is something like this. So I made a three-part blog on the Visual Studio blog last November-ish, where I identified this workflow as how you create your own bespoke tools using the clang-tidy infrastructure and framework. So we use a script to create a new check in clang-tidy itself. We identify which code we want to port. we create a AST matcher query, and we implement fix-it replacements. So, for example, the override check that we already saw has a matcher query for finding methods which don't have an override, and it has a fix-it to insert override into the places that it should be. And you do this again and again because you find new cases that you're not handling yet in your existing code, and then eventually you're done. You might be done when you have ported 100% of your code mechanically, or you might decide that 80% is enough, or whatever. Usually, you don't have to actually have the tool do 100% of the work. You just want it to do most of the work. So creating new check is something you do with a simple script that comes with clang-tidy. Let me just get that. Yeah. So we call add new check. So here I'm in the clang-tidy source code itself. So because it doesn't have a plugin system, we just have to build Clang and clang-tidy ourselves and change the source code. That's a bit unfortunate, but let's see if we can improve that later. So, so add new check, MISC, that's just a category, and make awesome is the name of my new check. So what that does is it creates some new source code for me, make awesome check.cpp and .h. It adds some documentation and some unit tests, and it says, done, now it's your turn. All right, what does that mean? So let's look into what it generated for us. Make awesome. So it's generated a new class for us, which has two virtual overrides. One of them is register matchers, and one of them is called check. And this class inherits from clang-tidy check. So that's the header file. Inside the source file, you'll see both of these methods. And essentially, to create a clang-tidy check, it's our responsibility to implement both of these methods correctly. And we can do those one at a time. So we need to write matchers. So here we see a matcher for the first time, function decal. And we bind it to X. I'm just going to change that to make awesome. So later, we take that make awesome text, and we take the AST node out of the result set, call it match decal. And if it doesn't already start with awesome, we insert the text awesome into the source code. So let's run that and just verify that it does what it seems to be doing. So I need to build clang-tidy now that I've actually changed the source code. That doesn't take too long. And once seems to be taking a little bit longer today. Once it's done anyway, I will be able to run clang-tidy with my new check. And you can see that it's giving me diagnostic output saying this function is not awesome enough. Here is the text to put in. And I can just add -fix. And it says the fix-it was applied. And I can confirm with git diff that indeed it has made these functions awesome. I can also see the existing awesome bar method was not changed because it already has that prefix. All right. Oh, the question was, do I have any callers for these functions?
Colors.
Colors. What's the problem with font colors?
Oh, no, there is nothing in it.
There's nothing in these functions. This is just test code. Yeah, there are no callers of these functions. And that's indeed a problem, because the only thing that my clang-tidy check does so far is it changes the functions. It doesn't change the calls. So my task now is to iterate. I'd probably need to add some calls, because I need to have a testable piece of code, and then add new matchers to match on the calls, and then port those as well. So that's what the rest of this talk is about. So I'm not going to get into that in the demo. So we can match any kind of code that we like. So far I've just matched function decal. I wasn't any more specific than that. I didn't say function decals which have a particular name or which take particular arguments, but you can do that. You can match on variables, functions, classes, members of classes, everything, instances, and particular ones by name, by type, by return type of function, by parameter type, anything that you like that's relevant to your refactoring need, you're able to match on. To do that, you need to actually make a matcher query. So that's where you write more complicated matchers. We've already seen the function decal matcher. This is actually a predicate language, so we can put stuff inside of it, such as is override. And that means match a method declaration which is an override. So the Clang comes with dozens of these kind of matchers, and you're able to extend them yourself quite easily. And there's a huge list of them in that website. Unfortunately, that's a little bit daunting, especially if, like me, you've never been a compiler engineer before, and you're trying to understand enough of the Clang AST and of matchers to successfully write one, which is actually quite difficult if you're not used to that. So here's just another few matchers. We can put has name inside of function decal, because functions have names. We can check the parameter, see if we can find a parameter with the name foo, and if that's true, then we match this function decal, and that means we can port it. But the problem is, because there's so many of these matchers, you need a way to discover them. Just reading the documentation is not enough, because there's just so many. It's kind of hard to understand what they mean. So what you can do is use clang-query. So here's an online version of the clang-query tool, but clang-query actually ships with Clang, so you can use it and type this kind of stuff into an interactive interpreter of clang-query to get it to produce output. So here I have the same code, but now I've got a few calls in there. And here I have function decal, which is the matcher we saw in our C++ code. And then below that, you can see that the function decal matcher has matched in each of these locations. So if I hover it, you can see on the left-hand side, the location is highlighted in the source. So I can go through each of these three. So if I want to know what matchers can I put inside of that function decal, I just write enable output matcher. And now for each of the results, each of the three results, I'm getting new content, which says if I add has body compound statement and then bind that to some name, it's going to match the line 3. Similarly, if I add has type lock, that'll match up in line 2. And type lock is a particularly useful thing if you're writing matchers. So I can also write has name for this particular case. I can say parameter count is 0. So this is how I discover that those two matchers exist. So I'll put that one in there, maybe. And actually, I'll change this to have a parameter. So now that's not actually matching. It's not matching bat because it doesn't have parameter count of 0. Right. So let's change that to 1 and actually match bat this time. So you can see down here, has name bat is now the thing that I can use with this matcher. So I'll put that in there as well. And at this point, I might actually be interested in the calls. So what I need to know is what are the AST nodes that represent those function calls? And the way to discover that is to enable AST output. So now I'm getting output of this AST tree, as well as my matchers, but that's just a little bit too much noise at the moment, so let's comment that out. And now I see only the AST for my result. And I can see that there's a call expr in there, and there's compound statement, and this kind of thing. So I'm going to want to port those calls, so let me get rid of my existing matcher and write a new one. Call expr, and now that's binding each of the function calls. So now I don't need AST output anymore. I go back to matcher output because I want to know what can I put inside of call expr. And down here, I see that I can use callee function decal. So let's paste that in. So now I'm matching call exprs, which call functions, which is all of them. But we learned before that I can put has name in here. So has name foo. And now I'm only matching calls which call the foo function. I'm not going to match the calls of awesome bar. So that matters because I want to match calls of functions which don't already have awesome so that I can add awesome at the prefix of each call, like that. So this is only doing the matching part of the check. It's not actually going to rewrite the source code or anything. But that's how you discover matchers now. You can type them into clang-query, have it output for you what is possible, and then you experiment with them. You see what does that actually mean. And so clang-query lets you inspect your code. It lets you sort of map in your head between what your source code is and how that's represented in the Clang AST. So this is a little bit futuristic because currently clang-query doesn't actually give you output of what the matchers are. You can only see AST output, and you kind of have to use that in the documentation to figure out what the matchers are. But you can use that Compiler Explorer website to find out as well. So once you've written your matcher, you need to implement the code to rewrite it. Implement the check part of your clang-tidy check, which actually does the rewrites. And it does that with this fixit API, which allows you to do insertions, removals, and replacements of your existing source code. So in order to do that, you need to specify where you want to insert, remove, or replace code. And to do that, you need to know the locations that are part of each AST node. So functions are represented with the function decal, and it has at least these locations bound to it, I suppose. Get begin location at the start, get location, which is where the function name is, and at the end we have get end lock. So the first thing you might think is, well, okay, if I want to change the return type of a function, I need to go to get begin lock and replace what's there with my new type. However, I think C++ 11, maybe it's 14, we can write auto here and we can write arrow int at the end. So now if I want to replace the return type, they have to go to get end lock. So there's something missing here, some kind of semantic location, which means the place where the return type is. And it turns out that's this big long thing here. So you don't need to concentrate or squint too much to see it. Well, you do need to squint, but don't worry about that. The point is, it exists, and we need some way of discovering what that line of code is. It's hard to come up with on your own. So there's lots of other AST nodes that are relevant in Clang. Here's member call expr. It has its own location, so it doesn't have a get location accessor as function decal does. Instead, it has get expr lock because it's an expr. So it's different. Then we have var decal, that's representing variables. It does have get location. It also has begin and end lock. And it might have an initializer like this. So the end lock could be pointing at a closed brace or anything. But another thing to note about locations is that they point to the start of the token that they refer to. They don't point to the end of it. So sometimes you have to extend your location to the end of a token. And there's a simple API to do that. You also have ranges in each AST node. So here is the source range of this entire function with 2 braces on the end, so it's complete. We get that with get source range. If we want to get just the signature part, we have this big line of code. If we want just the arguments part, it's this big line of code. And again, we have a discovery problem. Like, how are you ever going to figure this out? You need some way of navigating these locations. So once again, we can do that with clang-query. So instead of saying we want matcher output, now we say we want source location output. So now in the output section, instead of showing me the matchers that I can put inside of call expr and inside of function decal, it's actually showing me at each careted location what line of C++ code will get me to that location. So this is get begin lock, here's get location, blah, 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 the L paren lock, the R paren lock. So there are multiple source code strings which get you to the same place. And partly, let's change this to int. Partly that's it can look a little bit misleading. So here I see get begin lock, and I would think, okay, well that's where int is. But if I put oops, did that work? If I use const int, it's kind of split up the group of locations that used to be there before. Because the type spec start lock is actually the place where the int starts. Okay. Okay. So this is kind of how you would discover source locations. clang-query just prints out some C++ code, and we can put that into our clang-tidy check. And just have another look at that. Here I'm using get location of the matched function decal, and I'm saying create insertion at that location. Awesome. So this is the important bit that you would then discover using clang-query. What is actually the location I need to use? Okay. So once you've done that, you're going to have written a few matchers, and you think, well, that's great, it works, right? Let's say let's change this a little bit. Give it an int parameter again. And let's say I want to match function decals, has name, foo, and parameter count is 0. So this is just complaining because I don't have anything here. Cool. So it's telling me 0 matches. And I look at that and I think, well, it's foo, like that's the right name. Parameter count is right because it's before coffee time. Often you'll write a matcher and think, well, I think it's right, but it's not matching the function that I think it should be matching. So then you need a debugger. Let me just get rid of the output. So let's break on line 2. And clang-query tells us there's 2 new breakpoints after being inserted. One here for the function, and then another one here for the parameter. And then instead of matching, we're going to debug. And we get new output, which says, here is what happened when I hit that breakpoint. So when we hit this breakpoint on column 1, line 2, this is how that matcher was evaluated. Has name is green, that's correct because foo is right. Parameter count is 0, that's no, red. This is where we failed. So if I change parameter count to 1, it goes green, yay. And I can sort of just use this to debug my matcher. If I expect it to be matching some function or some result, why is it not working? So I can also see that the evaluation is short-circuited. So it stops at whatever the first incorrect matcher is, or whichever matcher is not giving you a result first. So yeah, that's pretty easy to use. Let's see. Let's just swap this around. Another thing we want to do is profile. So get rid of that breakpoint. Instead of debug, we're going to profile. So now I get new output again. It's telling me function decal was evaluated 25 times, but that's because in this source code, Clang built an AST tree of 25 top-level items. Each of them was checked to see if it's a function. And then 3 of those had parameter count 0, and 1 of them had name foo. So if I just include vector, you can see those numbers go way up. Oops. And it might be relevant to your matcher which order you evaluate things in. So here I've just swapped parameter count and has name, and I get 2 profiling outputs. Let's see if we can fit them both on screen. Yeah. Hopefully you can still see that, but here I'm checking parameter count is 0 1,000 times, and that passes, and then 291 times it passes, and we check the name of the function, versus checking the name of each function 1,000 times. Now, the reason that's relevant is you might, instead of using has name, you might be using matches name and be using regular expressions, and that might be a bit more expensive than just checking the number of arguments or parameters of functions. So you might find that if you swap some stuff around, your clang-tidy check runs a lot faster. Cool, so that's debugging and profiling. At this point, you should have all the discovery tools you need to write your own clang-tidy check. And then you need to run it on all of your source code. So you will test it on one file at a time, or maybe you'll create a dummy file to represent the kind of issues that come up while you're trying to write it. And then you try to run it at scale. And the way that you do that is you do need a compilation database. That's something that CMake and Ninja will generate for you. If you have a custom build system, you can generate it quite easily as well. It's simply a JSON file which lists all of your CPP files and how to compile them. You can also do some manual testing by just having a -- followed by compile command line arguments. So if I'm using Qt5, I would need something like this, and clang-query will then let me evaluate matchers. So if we want to run something like this over all of our source code, we might be replacing a type, and so we'd run it on one of our files. Oops. And that CPP file includes other header files. Now, if we change the types that exist in those header files, we're going to get compilation failures when we try to process the next CPP file, because the new type will already be in place in the header. This existing CPP file won't compile. So what we need to do instead is process all of the files, the CPP and the header files, put the results into a database, and then after processing all of the files, we use another tool called clang apply replacements to take those changes out of the database and apply them to the files. And when I say database, it's simply a YAML file in your file system that clang-tidy creates for you. So to run your clang-tidy check on all of your files, you would use this run clang-tidy script. It uses all of your cores. It does that replacement database stuff. It hides all of the complexity. And you can have it run on some subset of your files by specifying a regex as well. So that's how you, once you have a working clang-tidy check, or one that you think is working, you would run it on all of your code like that, and then iterate until it does fully work, or it does work for 80% of the time. So while I was doing this, I sort of noticed that if I use a compiler to compile some C++, I put my C++ file into the compiler, and it spits out some object file. When I'm using clang-tidy, I put my C++ file into clang-tidy, and it spits out a YAML file for this database. That's quite similar to how building works. So I thought, if this is what happens in a distributed build, can I just replace the compiler with clang-tidy, have it output YAML instead of object files, bring them back to my computer, and then apply them? So that's kind of what I found that I could do. I tell a build distribution network that my compiler is actually clang++ executable, but in fact it's clang-tidy. And it writes its result to an object file, but actually it contains YAML. So doing that, I'm able to run ice cream with clang-tidy refactoring instead of C++ compiling. So something that comes up when you're trying to write a clang-tidy check is you need to have all of your generated files be present when you're doing it. So for example, if you're doing something with Qt, you need all of your mock files to be present because they will be pound included. So you need to usually do a normal build before you try to do a refactoring build, say. But you also hit the same problems that you hit in a regular build, namely slowness. So it does help to do a unity build, just like it does when you're doing a normal build. It does help to use precompiled headers, and it does help to distribute your build over a network if you can. So I mentioned that the Clang query that you have on your system won't show you matcher output. It also won't show you source location output. It also won't give you the debugging features. It also won't give you the profiling features, etc. That's because I made a bunch of changes to Clang. So maybe I'm becoming a compiler engineer. I don't know. In order to facilitate those features. So I'm trying to upstream them. I was just at the Euro LLVM conference at the beginning of this week and showing these tools. And people there were very interested, and they want to review the code and get it upstream. So you should be able to get the benefits of these features and write your own checks in the next few months. So a few things that I created is the debugging interface that allows the debugging and the profiling. I also am working on output independent data. So up until recently, inside of the Clang source code, you had something called an AST dumper, and that's what gives you the AST output that you saw in clang-query. It traverses through the AST that you give it, and it just prints that out to a stream. So what I've done, and this is already in Clang upstream, is I've split the AST dumper into two classes, a traverser and a separate node dumper interface. That means that we can still output to stream, like you see in clang-query, but now we can also write a JSON node dumper and dump that stuff as JSON, which is maybe machine readable. We could also dump it as XML or whatever. But that separation of concerns means that I have a generic tree traversal class for Clang ASTs. And any of you who know me from my Qt contributions, what do you think I would do with that? Ivan is smiling. So I did a lot of work in Qt with QAbstract item models. So once I have this generic tree traversal interface, all I have to do is implement a class which implements the node dumper interface and implements QAbstract item model, and then I can put the Clang AST into a Qtree view. So that enables UI tools for processing the Clang AST. So that looks something like this. So I have a bunch of files in this project, CPP files, and I can select any one of them. And once I've done that, I can look through the files that are included by this CPP. So if I stick with main for now. So I select a file, and on this side, I get the AST for that file. So it filters out all the header file stuff, the noise maybe that I'm not interested in. And I can click around, and maybe you can see this cursor moving as I click. So here it's after return, and here it's on the compound state, the brace there. So it kind of is, again, just sort of a useful way for me to discover how does the Clang AST map to my source code. So you can click and see it very directly. If I look in a header, the AST changes here on this side, and again, I can just explore. But why stop there? Because clang-query has this sort of dynamic evaluation of AST matchers, I can simply use that in my UI as well. So what I have here is sort of a scrubber kind of tool. So if I click on this matcher, I get the result here then on the right-hand side. And I can click on each one of those to see the results. So these two results are in the header. This one is in the main.cpp. And I can click just to see how they actually relate to the source code again. But just like I showed on the compiler explorer, I can see matchers instead of AST nodes as well. So, you know, for this method or for this, this function, I can see all the matchers that I can put inside of it and still get that particular function as a match. I can also see the locations of each of the result nodes. And what I can do as well is actually click around in the source code on these, circles, sort of like radio buttons. And you see on the right-hand side, my selection is changing. So this is, again, the C++ that you would need to use to access that particular location. So that's, again, just showing you very directly, here is the code, here is the location you get if you use that code. Next thing I might want to do is debug, so I can do that as well. But I need to set some breakpoints. So I'll just click on the side here, and I get some more of those circles. I actually call this the stethoscope tool because it's kind of like a doctor's stethoscope in that I can click around and breathe, and it sort of shows me this time in my matcher source code, whether my match actually matches, where my matcher actually matches. So if I make it not match, my source code goes red, and I can make it green again. So yeah, those are just the debugging features that we saw in clang-query before. Profiling works exactly the same way as well, so just a hit count. The profiling, unfortunately, doesn't give you time, because the thing that takes a lot of time is very tiny time increments. So I think I'm just hitting floating point errors when I try to accumulate those into something meaningful. So, okay, now I have a UI, which is very directly showing me whether my matcher is working, what source locations I can put into my C++ code. Why stop there? Why not run clang-tidy in this UI? Now, some of you may have noticed my wristband, and some of you will have noticed the bug in this code. So what I've written here is a matcher which just matches any variable which is const qualified or is a reference to const, and I'm binding it to something called port const. So I've pre-written that because it is a little bit complicated, but you discover how to write that in the exact same way as before. Just explore and have the tool show you the matchers. So below that, I have some JavaScript. I'm getting port const out of the result nodes. Removal start is get begin lock, because what I want to do is remove const from here and put it on the other side. That makes it const correct. So, this tool could be made to run in reverse, but you wouldn't want to. So on the right-hand side, then I have result. So currently, const is still on the incorrect side here. So let's see what we have to do to make a tool which fixes the location of the const. So yeah, first we want to remove the const. So we want to remove from this, well, that's no good. We want to remove let's use this to show me the locations. We want to remove from this location, which I can see is called getBeginLock, to this location, which I can see is getTypeSpecStartLock. So I can just right-click and copy that location. That copies it as text, and I can fill in this to-do. And you can see on the right-hand side, the const is now gone. That's because this JavaScript code is being executed live as I change it. And the change is being applied. So I can see the source, and I can see the diff just to see what's actually being changed. But it's also recompiling this. So it's actually verifying that after doing that removal, everything still compiles. So if I would try to remove up to this location, which is get location, I suppose. I'm getting compile diagnostic output from the tool. And that's because I've removed too much. But the interesting thing here is it's not writing the files on disk. It's writing these result files to an in-memory file system overlay and then recompiling using that. And that means that you're not going to be touching your headers, so you won't need to be recompiling a lot of stuff when you go back to C++. Okay, but we've only done part of the job here, so let's again, we're just removing const. And now we need to find the place to insert the const. So going back here to the query location, it looks like we want to add const at get location. So let's try that. So this is JavaScript, so var import lock equals port const dot get location. I also get JavaScript diagnostics whenever something goes wrong. So I'll fix that and that disappears, and I go back to my output, and I see my diff again, and I haven't actually inserted anything yet. So let's copy this diagnostic. This diagnostic is going to be active at insert lock. I'm going to say insert here. And instead of create removal, I create an insertion rule at insert lock. And what am I going to insert? Const. Sorry. And if I go back to my output, you can see that const is now in the correct place. I haven't put Clang format in here, so I put a bit more white space in there than I should have. That's not a big deal. I assume you're already using Clang format, and it's kind of nice if you don't worry too much about the white space in these kind of checks, and just have Clang format handle that for you after. Okay, so this has actually changed two files. It's changed my main file, but it's also changed the header file, because that also has a use of incorrect const in it. So here it's const adder, and here it gets changed to adder const. Cool, but I have multiple files in my project, is one of the remaining problems. Another one is, all I've shown you is I can rewrite the source code and put it on screen. You need to get it into your source code repository. So there's one more step that you need to do for that, and that's bulk porting. So here I can filter out which files I want to run my tool on. As it happens, I want to run it on all of them. So this is the exact same checker we were just looking at. It's the exact same JavaScript, so it should be doing the right thing. And I can click run. Maybe that's hard to see. I can click run, and it runs, the JavaScript for all of my source files, and gives me an indication of whether the recompile after changing those files was successful or not. So 3 of them were successful after changing the const. I can then look through each of the files to see what the actual change was, and I can see the diff and everything like that. And then once I'm happy, I can write out the changes to disk. But this other file, actually, it didn't build after running the tool. So something is wrong. So let's have a look back here and change to look at other file. And you can see that it's using const int ref. And I'm getting my recompile diagnostic. I can see what actually is going wrong. It's putting the const in the wrong place. And I can see that in the diff as well. So the reason for that is actually because of the ampersand. And sorry. And actually fixing it is not so interesting. So I'm just going to here we go. I'm just going to put in the correct code here. So that's just checking a different location and putting in the const at a different location. But my point here is my cycle doesn't involve recompiling C++ anymore. Previously, if I would create a clang-tidy check and something goes wrong, I have to go back to my clang-tidy source code, change the C++, rebuild clang-tidy, and then run the tool over all of my source code again. Now I don't need to do that. I'm still in the same UI doing JavaScript, and now I'm getting int const ampersand. So if I go back to my bulk port dialog, I hit run, everything is green, good. I can look through each of the changed files and see that they're now using correct const. And then I can, I can hit the write out button and go back to my console. And you can't, well, I'm not even sure if that's, yeah, that is the right project, but with the colors you can't see. But I'm just showing that indeed the files have been written out. So now I can rebuild this and it should all work. And I can check that in. Great. So just one note about that demo. It can be quite common to create tools in Qt which start with a Q as their name. And one of the comments that I got when I was blogging on the Microsoft Visual Studio blog about how to create clang-tidy checks, somebody left a comment saying, Clang sounds like a Klingon general. And so that gave me an idea. I was like, okay, well, I want success in my automatic refactoring. So any Trekkies here? What do you think I called it? Kapla, right. So that's strange, an empty slide. That slide should not be empty. Okay, well, what I wanted to show was this exact diagram, but bigger. So what I'm showing is the workflow is the same with this tool, but with this tool, the entire development cycle is much tighter and smaller. You don't have to recompile stuff because it's not C++, and it's a lot easier to use. Cool, so that's all I have to say about tools when you're creating clang-tidy checks. Are there any questions at this point? Yeah.
I was wondering how clang-tidy and the text script with preprocessor macros, some of your thing generated by macros or some other component.
Yeah, so the remark is macros throw the cat among the pigeons here. Macros make it hard to do this kind of thing, and clang-tidy can allow you to handle macros. I'm not going to cover that here because it is quite advanced. Again, I've hit problems where it just is not worth it trying to handle macros in that case, and that's where I declare this is my 90%, and I'm going to handle the rest of that stuff manually. So yeah, macros are difficult, so are templates, actually, template instantiations. But I think the latter can be made easier to handle. Another thing that might be on your mind is, can you use that UI tool? So I do want to make it open source, put it on GitHub and all that. One of the problems with that is it's largely in one file, one big class with multiple responsibilities, lots of copy and pasted code, commented out blocks, which may or may not mean production code, but it's too messy at the moment to actually publish it. Another reason not to publish it right now is that it depends on all of the Clang patches that I haven't put upstream yet. So hopefully within the next few months, this will be available to you. You can just download it and build it. Yeah, Alistair.
Don't you have a tool to help you with refactoring that?
Yeah, I do have a tool for that. Yes, another question, Peter.
The changes that you do, it's all location-based. So you fiddle with the location to figure out. You cannot say, take this AST node and replace it by something else.
Okay. Okay, so the question is, well, it's a remark, so I'll rephrase it as a question. The question is, why are we doing this location-based replacement of source code instead of doing more high-level changes based on the AST nodes, right? So I actually have a demo to answer that question. Let me just, I kind of decided to take this out of the presentation, but because time-wise we're doing okay, I think I'll just put it back in. But I do have to rebuild my my UI. So recently, Google has been doing a lot of work on this sort of make it easier to do big refactorings problem. So they've been working themselves on new APIs that are going into Clang, and they've been sponsoring students to do that kind of thing as well. So one of the things that just got upstream is called the transform library. So again, I have a bit of UI for that. So I have a matcher for the multiply function. And I'm just adding another binding, another binding for the parameter just to show you what happens when you have two bindings. So down here, I click Add Transform, and I can select one of my bindings. So I select the parameter, say, and I say I want to change the node that was bound, and I replace it with empty, nothing. And you can see, it's kind of strange. Yeah, you can see that I'm actually removing the parameter that I was bound. So in this case, I don't have to use source locations. I could also just add another transform for the multiply function itself and replace the name with something. And it's replacing the name in the output. So yeah, this might be easier than doing all that messing with source locations, but it's also a little bit constrained by what the people who create the transform library make possible. Peter, does that answer your question? A little bit. So this is under active development. They do have like a template language and everything for this, so that you can use variables and sort of manipulate the name and then put it back in. So that is also just something that's in the future for your clang-tidy checks. Yeah.
So far, it seems like you can match on full strings, or say, as two parameters, change the name. You think a little bit more complicated, like match a particular predicate. I have more than two parameters, or change the name by removing all characters. It seems that the API is like direct match to factor.
Sorry, could you rephrase that? Or?
Yeah. Can you do more predicate-based matches for the nodes? For example, has greater than 3 parameters.
So the question is, can we are there more predicates that we can use in our matchers, such as instead of parameter count is, can we say parameter count is greater than this and less than that, or whatever? And the answer is today no, just because nobody has written that. But the answer is also yes, because you can write it even if you only keep it in your own source. So the matcher API is extensible, and I'll be looking at that a little bit in slides. Any other questions at this point? Okay. So that's the tools part done. Let's look at some tips, tricks, and traps. Stuff that you'll encounter as you try to write your first or maybe even your 100th clang-tidy check. So when you're doing this, my advice is to focus on porting expressions. So you'll find a function that you want to change, and that's a function decal. So maybe you want to rename it. But then you need to change all of the callers to use the new name as well. And those callers are expressions, they're not declarations. So that's one of the things that I just didn't know when I was first trying to create clang-tidy checks is what is a declaration, what's an expression, what's a statement, you know, what's the difference between expressions and statements. So yeah, you should focus on porting expressions because that's harder and you have a lot more of them. You should know that expressions reference declarations, so I have some slides just to illustrate that. You should get familiar with all of the AST classes just by dumping the AST, looking at how things are made up, and sort of getting familiar with them in that way. You would need to know that there's a call expression, and you need to know that there's a member call expression, and they're different, and you know there's more source locations and more matchers that you can use with them. Types are generally easy. You just use the as-string matcher to say, I want a function which returns a type of class foo. So that's generally quite easy. So just to illustrate the relationship between expressions and declarations again, here's some source code. I have a foo function and a bar function, and foo contains a call to bar. So in this, the call expr is bar. That's the only call in this source. And function decals, I have 3 of them, even though I specify foo twice. This is a declaration. This is a declaration and a definition, because it's the definition of the function. And they relate with the callee matcher. That's something that you can discover just by dumping the matchers and seeing what's what. So if I have a call expr, I can put in callee function decal. And the function decal relates to exactly whichever function is being called. Decal ref expr is, what is it? Expressions which reference declarations. So here in this source code, all of the circled elements are decal ref exprs in the Clang AST. And here, var decals and parameter var decals are circled in the source code as well. So obviously, var decal is the declaration of the variable. And so the two are related with the to matcher. So if I have a decal ref expr, like I would write to var decal to get from this I to this one, the actual location where it's declared. And I need to do that all the time because here at this point in the Clang AST, we don't know the type. It's just not encoded. But we know how to get to the declaration of the variable, and that's where the type is specified. So that's where we go when we need to find out what the type of something is. Again, member expressions. So in this case, there's 2 ways of having members in your source code. One is a.member, and another is just member, where the A is explicit because foo is in A. So these are member expressions. Member data is called a field decal in the Clang AST, and the 2 are related again with member. So if I have a member expr, I can put member field decal in there and then check the type of the field decal or the name of it or anything. So just a summary table of those 3. And I'm just showing you this because these are, first of all, they're kind of hard to discover, partly because they're not all the same. It would be nice if I could say, if I could use the to matcher between call expr and function decal. And you know, the middle column would just be 2, 2, 2. You know, a call expr to the function has name bar. But so these are a little bit hard to discover, and you use them all of the time. You know, anytime you're porting an expression, you need to use one of these matchers. Another thing that might come up when you're writing your matcher is something like this, this problem where you want to match all of your classes, and you want to match a method foo if it exists. So here, record decal is something that matches structs and classes and unions. Method decal obviously matches methods. So I'm binding the class or the struct that I find with class decal, and I'm binding the method that I find with method. The problem is not all of the classes that I care about have a method called foo. So I want to optionally capture foo if it exists. And the way to do that is to wrap the method check inside of any of and pass both the method check and anything. So anything is a special matcher which just matches everything, including nothing. So here, this is how you express match records with either methods of that name or not, okay? But if it is found, then we bind it. So that means we're going to be able to capture that later and rewrite it, which is probably what we want to do. And the way we do that is like this. So we get the class decal out of the result set. We get the method out of the result set if it's not null, and then we process each of those elements with locations. So another thing that we can do is, if we have our C++ code with a big, long, nested matcher, we would want to refactor that, partly because we want to reuse parts of it. And we can do that by just assigning it to an optional variable in C++. So here I have my any of the method, and then I can use that in place of where I cut it out of. So that's quite easy. But another thing I can do is I can create my own matchers just using a lambda syntax like this. So optional takes a matcher and it puts it into an any of together with anything. And that means that I can just use it in my regular matcher code. So I have a record decal which optionally has method of name foo and binds that, and otherwise I just bind my class. So optional is quite a useful utility to have in your tool belt. If you want to create AST matchers in the way that they're done in the Clang source code, you'll see these macros for that. And you can extend that with your own matchers as well. You might have something very specific to your source code, is a reflected type or something like that. And you have some convention for reflected types so that that's easy to determine. So you would be able to write, record decal has name this is reflected type. So you can extend it in your own way. So another problem that you'll have if you have a very large source code base is changing, say, 10,000 files with millions of lines of code all at the same time is quite hard. And what you might want to do, instead of just doing that in a big bang, is do what we call evolutionary refactoring or non-atomic refactoring. And essentially that just means add the new API, port the code to the new API away from the old API, and then finally remove the old API. It's just doing all this over a longer time frame. And there's a lot of reasons to want to do that. For example, if your CI fails, you have to try to revert this huge patch, and maybe something else got in the meanwhile, and you'll get a merge conflict trying to revert your huge patch. Also, you might want to revert it in 6 months instead of 6 minutes, and that would be very difficult as well. So it's better still to try to create smaller patches for your source control system. Some of the ways that you can do that is you can use clang-tidy, and you can tell it to filter to port only particular header files. That allows you to exclude a lot. You can also just decide to write multiple clang-tidy checks. That's what I did. I wrote one for porting variables, a different one for porting fields, a different one for porting parameters, a different one for porting return values. And this is when I was trying to replace one type with another. So types appear all over the place in C++. And by doing that, it was the least disruptive way for my team that I could do that refactoring. But there's still a bunch of traps that you encounter. In this case, I needed to port different kinds of parameters in multiple steps. So here I have my string s, and I call foo and bar with that s. And today that's fine. But I want to port to your string class because your string is better than mine. So I might, implement my rewriter to rewrite this line as your string s. And for the call to foo, that's fine because my string converts to your string. So I control my string, and I just add an implicit conversion to make the source code work. But because bar takes my string by reference, this would not compile anymore. So I needed to have two steps. First, I just ported calls which don't take the argument by reference. And then after that, I did another pass where I ported the calls which do take it by reference. And the reason for that is I needed to change both the variable and the parameter at the same time. So those are coupled. You get a similar problem with methods that return references as well. GetString here returns a const reference to my string. So if I would have a caller of getString, which maybe it's the implementation of getString, I think. Yeah. I can't just change its return type. I also have to change the type of the field. So again, those two things are coupled in a way that makes it hard to do that kind of evolutionary refactoring. It's still possible. You just have to change the coupled things together. Another trap that you might hit is if there's an external class, like let's say I'm using your string anyway because I'm using your library and you have some interfaces where it appears. No, I guess that should be your string. Anywhere that I'm implementing your interface, I need to make sure that I don't change the type. Maybe I'm explaining that a little bit backwards, but you get the idea that if I want to change all of the methods parameters in my source code from my string to your string, I can't just change interface implementations as well because the external class is still using my string instead of yours. So you can exclude overrides with a simple matcher like that. And finally, the last trap I think that I show you is the performance trap, where I have all these, I'm in the middle of porting my code between my string and your string, and I'm at a place in the refactoring where I've got getString returning your string, and I've got processString taking your string, but my variables are still using my string. And that means I'm doing all this conversion of these strings, and that can be quite expensive in terms of performance. It can still be correct, and it can still compile, but it might be slow. So that's just something to keep in mind as you do this. I have one more element, actually. How would we match this kind of source code? A equal B. If you just create some test code and run clang-query on it and just investigate what kind of matchers you get, you might get a few different options depending on what source code you actually put in. So here I have two ints, a equal b. Alternatively, I could have struct a with a member operator, or struct a with a external operator function. And it could still be a equal b that I have in my source code somewhere. So if it's ints, then those two are related with a binary operator. You can discover that. But if it's those structs and the member operator, we can't use binary operator anymore. Instead, it's CXX operator call expr, has overloaded operator name. So that's just sort of a problem that you'll hit into if you try to port this kind of code. But luckily, independent of whether that operator function is in the struct or outside of it, the matcher doesn't change. So that's at least good that you only have to handle 2 cases instead of 3. So just to summarize this whole talk, large refactorings are possible in your code base, even if your code base is very big, even if your needs are very bespoke, even if you have macros and reflection and doing all kinds of special things. Refactoring it and opening up new maintenance possibilities are possible in your code. The tooling for this is changing in the near future. You'll be able to get all the tools that I've been demonstrating, and hopefully you have seen that they make it quite easy to do this kind of large mechanical refactoring. So do keep in mind that clang-query exists. It's not very well documented as a tool that's essential to creating clang-tidy checks. Do use the reference. It becomes more tractable once you're familiar with some of the matchers by playing with clang-query, even though there's like hundreds of elements there. And do, if you can, distribute your refactoring workload with something like Ice Cream, because running clang-tidy does take as long as compiling your source code, so it can take a long time. With that, I'll take any remaining questions that exist. Just to point you to some more resources, the compiler explorer that I showed is at my website, so cestevera.com. You can read my blog, you can see my Twitter. If you look on the VC blog, you'll find my old blog posts, my series. Do use Stack Overflow. If you learn something, share it and blog it on Twitter, anywhere, just so we can share the knowledge about these things. So, if you have any questions, and if I have a clear expression of an answer, we can go through that now.